Hi, this is Sonia Doucette. In this video, I'm going to talk a little bit about the meaning of the 4 different types of quantum numbers and also how to determine them using some simple formulas. So the first quantum number is n, and this is called the principal quantum number. And this quantum number tells you about the size and energy level of an orbital. For example, using the Bohr model of the atom to illustrate, here's the nucleus, here's the first energy level, that would be n equals 1, that's the energy level that's closest to the nucleus. The next one would be n equal 2, which would be a higher energy level, and so on, n equals 3, n equals 4. So the next type of quantum number is denoted with the symbol L, and this is called the angular momentum quantum number. And this defines the three-dimensional shape of the orbital. So for example, L equals 0 indicates that you have an s orbital, which is a sphere. L equals 1 indicates that you have a p orbital, which is a little more complicated. So a p orbital has 3 suborbitals or lobes along an x, y, and z axis. So one of the lobes falls along the x-axis, and that entire lobe can hold 2 electrons throughout it. The second lobe falls along the y-axis, and they're all the same size. I'm not the best at drawing. And then the third suborbital lies along the z-axis. So there are 3 suborbitals there. Each of them kind of looks like a bow tie. And then if you have an L equals 2 angular momentum quantum number, this indicates that you have a d orbital, and I'm not going to try to draw that one because they get more complicated as they get bigger. And L equals 3 indicates an f orbital, and so on. G orbitals, H orbitals, they exist, so you can keep going. And again, the f orbital, like the d orbital, is harder to draw, so I'm not going to try to do that. So to determine the possible values for L, you use the following formula. L is equal to anywhere from 0 all the way up to n minus 1. So, for example, if n is equal to 3, the possible values for L are anything from 0 all the way up to 3 minus 1, which would be 2. So possible values for L are 0, 1, or 2. Next one is, the third quantum number is m sub L. That's the symbol used to denote it, and this is called the magnetic quantum number. So this defines the spatial orientation of an orbital with respect to a standard set of x, y, and z axes. So I'm just going to write spatial orientation and then explain this a little bit more through an example. So let's look at the p orbital again. And each, again, there are 3 p suborbitals, one along the x-axis, one along the y-axis, and one along the z-axis. So one of these, let's just say the one along the x-axis, is going to be the m. Let me show you how to determine them first. We need to do that first. Going back. So determining the values for the m sub L quantum numbers. You use this basic equation. They can range anywhere from -L including 0 and going all the way up to a positive L. So in the case where L equals 2, if we look at this case, the possible values for M sub L are -2, -1, 0, 1, +1, and +2. So there are 5 possible values there. If we look at another example, so for the p suborbital, L is equal to 1. So the possible values there for M sub L are going to be -1, 0, and +1. So notice there are 3 of them, and there are also 3 suborbitals for p orbital. So one of them is going to be designated as M minus 1, so we'll just call that the y-axis. One is going to be denoted as M sub 0, we'll just call that the x-axis, and then the other will be M sub +1, and that would be the z-axis. So those M sub L values, those magnetic quantum numbers, are referring to the suborbitals of a p orbital in this case. In this example where we came up with 5 different possible values for M sub L, that would be relevant to a d orbital. So d orbitals have 5 suborbitals that, again, we're not going to try to draw because it gets complicated fast. And finally, the last quantum number is denoted with an M sub s and is called the spin quantum number. So this describes the spin of an electron. So in any given orbital or suborbital, so an s orbital or 1p suborbital, for example, it can only be possible for this M sub s quantum number to have 2 possible values. It can either be +1/2, which is called spin up, or -1/2, which is called spin down. So let's look at the p orbital again. And let's say it's a p orbital with an energy level of 2. In that case, n equals 2 and L equals 0 or 1. In this case, L would have to equal 1 because it's a p orbital. And the possible values of M sub L we already looked at would be -1, 0, and 1. So if you go further, the fourth quantum number is M sub s. So you have to determine this value for each of those suborbitals. So basically you can fit 2 electrons in each of these suborbitals. So for example, in this M sub 0 orbital, suborbital, you're going to have 2 possible values for where electrons could reside. One's going to be +1/2 and one's going to be -1/2. So that would be 2 sets of quantum numbers. So remember, it's a p orbital, so L is equal to 1. So if n is equal to 2, L is equal to 1, M sub L is equal to -1, so let's pick the y suborbital to look at. So there are 2 cases for M sub s in the y suborbital. This first one, and you'd have one case where you have +1/2, and then another set of quantum numbers also relevant to this suborbital residing along the y-axis, and that would be n is equal to 2, L is equal to 1, M sub L is equal to -1. Notice everything's exactly the same except the M sub s is equal to -1/2. So you're in exactly the same energy level for this, exactly the same p suborbital, and exactly the same p orbital, and exactly the same p suborbital. The only difference is that one orbital, or one position for an electron within that suborbital has to have a spin up, and the other electron that could reside in that suborbital has to have a spin down. So you can look at these as different addresses for an electron that could fit into that p suborbital at the n equals 2 energy level. And that's it.